Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is space-time. And back again this month to talk with us about this topic is Tim Campbell. Welcome back once again, Tim.
Thank you, Don. Pleasure to be here.
Yeah, we're always glad to have you. So, space-time, what can you tell us about that?
So in our last episode, we discovered that light actually had a speed, but we left it off with a bit of a conundrum, which was that the speed was always measured to be the same, even when it should not be. And so enters a guy who most people have heard of, Albert Einstein. Now, Albert Einstein wrote a lot of papers, and in 1905 was a good year for him. But one of the papers is called On the Electrodynamics of Moving Bodies, a very complicated name. The short name that we use today is special relativity. Now, there's special relativity and general relativity. General relativity is more complicated. We're not going to talk about that on the show. But special relativity is fairly easy. High school math is more than adequate to get by with what we'll do.
Good.
So he's going to suggest two ideas that will be put forth. One is that the laws of physics are the same for everyone, everywhere. That doesn't sound very controversial.
Sounds reasonable.
The second one is that the speed of light will always be measured to be the same for everyone. Now, that's an idea that could be controversial because if I've got a light on, say, a lamppost that's not moving and a light that's, say, the headlights on a car flying down the freeway at high speed, you would think that the light from the headlights is coming at you faster from the moving car than the lamppost.
Sure.
But what Einstein realizes is that there is actually a distortion in time that's going on, and we'll get to that. But what special relativity does do is a guy named James Clerk Maxwell comes up with the idea of electromagnetism, electricity and magnetism being two sides of the same coin. Special relativity ties light into the action. So now the rules of classical mechanics, the rules of light, and the rules of electromagnetism are all neatly packaged together in this theory.
Okay.
It is special because it ignores gravity, so we're going to leave that out of it. That paper was called The Field Equations of Gravitation. That's the thing that everybody today calls general relativity. So that's a cool topic in and of itself. There's another character in the story. This is a guy named Hermann Minkowski. Now, Minkowski is one of Einstein's teachers. But more importantly, Minkowski is a brilliant mathematician. So this is one of these people who can just look at an equation and visualize in their head what's going on. If they want to turn the equation around in all sorts of different areas, they can do that. And so what he does is he's looking at Einstein's equations in his paper on special relativity, and he realizes that it's pretty easy for him in his head to use this to represent special relativity as four-dimensional space-time, and he can do this graphically. Einstein's not super keen on this initially, but once Einstein looks at what Minkowski is doing, he realizes that this is a very convenient tool, and it really does simplify things.
Interesting. So are we going to fill our viewers in about this?
Yeah, so to come up with this idea that time does not flow at the same speed for people. So that's that's the root of his idea, is that everyone thinks that the speed that clocks tick are the same for everyone. And Einstein says that's not necessarily true. Those clocks might not tick the same for you as they do for me if our circumstances are different, our point of view, which is why they call it relativity. How am I different relative to you? And so the way you would measure time is how much time has passed between two events occurring. And so we have to have two events. So event 1 and event 2, and they're going to occur at time 1 and time 2. They're also going to occur at location 1 and location 2. And the equation that they come up with is this thing called the equation for the space-time interval, which is how much time has passed between the two events, given the space between where they occur, like the start of a trip, the end of a trip would be one event and the other event, or the time, when did you start the trip and when did you complete the trip. And if you crunch the math, what everyone will agree on is not how much time has passed, but they will agree on the result of the space-time interval, the way he has figured this out.
So sounds kind of complicated.
It's only a little bit complicated, and my goal today is to show you a cool little trick where you can actually figure out how time distorts and not have to do any math at all.
Oh,
so that is
okay.
actually kind of convenient.
Okay.
Now,
so we're going to hold you to that.
and now we're going to use some special graph paper to get this done. Now, we'll show our viewers briefly one version of the equation for the space-time interval. What you can see in here is that we need to know how to square things, we need to know how to take square roots, and we need to know how to multiply, add, and subtract. But that's all we need to know how to do. We don't need to know how to do anything fancier than that. And I'll get to more on the equation for the space-time interval later. But let's do a little game to make it easy for people to get their heads around how time distorts.
Okay.
All right, so we're going to pretend that we're going to take a little trip on a bicycle. So I've got a small town that's 10 miles by 10 miles. And I'm going to start my trip by pedaling my bicycle at precisely 10 miles an hour. And I'm going to pedal heading on a trip going north. And I'm only going to go for 1 hour. And at the end of 1 hour, I'm going to stop. And the question is after pedaling for 1 hour going north at 10 miles an hour, how far north am I? And it's not a trick question.
Yeah, 10 miles.
10 miles, it's pretty easy. By the way, how far east did I go?
You didn't.
I didn't go east. I wasn't going east, I was only going north. Okay, well, I could do the trip again, and this time I could pedal my bike east, and then at the end of that trip, you could say, well, how far east am I? And it would be 10 miles. And how far north am I? And it would be none. I didn't go north. But what if I decided to go northeast?
Okay.
So if I take my bike on a northeast trip for 1 hour at 10 miles an hour, at the end of my trip, something interesting happens. I don't actually make it a full 10 miles north. I also don't make it a full 10 miles east. What I actually do is I end up about 7 miles north and about 7 miles east of my starting point. I am 10 miles away from my starting point. That much is true. But I've traded a little bit of my north progress and my east progress for each other to get this compromise. And this is giving us some insight into what's going on. So we're going to do exactly the same problem, but this time we're going to relabel the graph. And instead of north and east, we're going to say that in one direction we travel through time, and in the other direction we travel through space. And when I label the graph, I'm going to decide that the time direction will be measured in years, and I'm going to decide that the space direction will be labeled in light years.
Okay.
Because that makes it easy.
Sure.
Okay, so if I get in, if I don't get in a ship, if I just sit right here in this chair for 1 year and I don't move, at the end of a year, how far have I traveled through space? And I haven't traveled through space.
No.
I was staying right here the entire time. But I have been staying here for a year. So how far have I gone through time? Well,
one year.
it's a year later,
Yep.
right? So I've gone 1 year through time, but I haven't moved through space at all. Okay, well, I could do another thing. What if I could travel at the speed of light? Now, it's not actually possible for anything that has mass to travel at the speed of light, though it is possible for it to come close. If you are massless, like light doesn't have mass, so light can go at the speed of light. That doesn't break any rules.
That's why it's called
Light,
speed of
speed
light.
of light. But if you have mass, you can't do that. But we're going to ignore that rule and pretend that we can travel through space at the speed of light. If I travel at the speed of light for what you would say is 1 year, how much time do I think has elapsed?
Okay.
And the answer is, time has not elapsed. I simultaneously left from my origin and arrived at my destination without time occurring. That's a bizarre concept.
Yes, it is.
Okay, but what happens if I decide that I'm going to do a little bit of both? So I'm going to travel at some portion of the speed of light, a pretty significant portion of the speed of light, for what you would say is 1 year as the non-traveling person. I, as the traveling person, will think that something less than a year has elapsed. and we will disagree on the amount of time. And that is because I'm trading off a little bit of my ability to go through time for my ability to go through space. And it works exactly the same as that bicycle game where we went at the 45-degree angle, we went northeast.
Sure.
So we're going, on that angle through time. And that is the essence of this trade-off, is that the faster you go relative to the speed of light, the slower your clock will tick.
Okay.
And so you've got the essence of the problem. If you can understand that analogy, how we compared it to the bicycle trip, you understand the essence of how time distorts.
Oh, okay. So, yeah, we could do that without math.
Yep.
Okay.
So now we'll just go one further, and this is the part where I tell you that in the previous few minutes I lied to you because I made it sound like it was just a simple matter of the geometry of a circle. Did you go this way or did you go that way or did you go to a 45-degree? But they all, if you take all the directions you could go, they all, and put all the destinations in there, it would form a curve or a circle. It turns out, and this is where we mentioned how Minkowski was brilliant as a mathematician. So I showed you that formula for the space-time interval a little bit earlier.
Sure.
If I put up that equation again, and I want to put it up with another equation that anyone who's been through high school has probably seen, and that's in geometry class, you learned the formula for a hyperbola. And so for a hyperbola, and I've colored these things orange, purple, and green. You've got something squared equals something else squared minus something else squared. Okay, so those are the three things. So everything is squared, and it's always something squared minus something squared equals the other thing squared. And when Minkowski looks at that formula, he says the space-time interval is the space-time interval squared equals the difference in time squared, the time from event 1 to event 2, and minus the difference in distance squared, the origin point and the destination point squared. He said that's a hyperbola. And so he realizes that he can represent this geometrically. You can draw this out. And so to do this, I promised I would show you how you could calculate time distortions and not actually do any math. So I showed you an equation. We're not going to do the equation. We will, just to keep me honest, but you're not going to do the equation. So what we need to know is those little triangles, that means delta. That's the Greek symbol for delta.
Right.
We use that to mean difference in math. The difference between time or the difference between the distance, the locations, if you will. And we have this term called c in our equation, and we want to get rid of it. So c represents the speed of light. And the speed of light is could be represented as the 299,792,458. That's actually the speed of light down to with 0 round off. We could do it in miles per second. We could also do it as light years per year. And the trick gets cool because in light years per year, the c becomes a 1. And now the equation is 1 over 1. And in 1 over 1, anything times 1 is just an unchanged thing.
Right.
So we can literally just get rid of that from the equation, and that makes it really easy. I have a piece of graph paper showing all these hyperbolas drawn through the axis of each point on the x and y axis. I have a hyperbola going through. They asymptote toward a 45-degree angle. So you'll see all the lines getting very close. The curves get very close to the 45-degree angle line. They never actually touch. We'll have an origin point that we'll draw, and the diagonal line is the speed of light. If you could be on that diagonal line, you have achieved the speed of light. We'll label our axes for years and light years, and we'll go with that. So here's our example. They love to use Mary and Bob. I don't know why they use Mary and Bob in every physics problem, but they do. Mary is going to be our observer, and Bob will be our traveler. So what we're going to do is Bob's going to get in a rocket ship and travel at 2/3 of the speed of light. And when he does this, Mary is going to stay still, not travel, and we are going to draw a slope where we go 2 over and 3 up to represent our 2/3 of the speed of light. And Bob's going to take the trip. We'll draw a 10-year point for Mary and just draw that across the graph. And we'll wait to see when Bob intersects with that line. And when Bob does, we're able to ask ourselves, how much time does Bob think have elapsed? All we have to do is count the curves on that graph paper that Bob's line crosses. And so if I do that, I get 1, 2, 3, 4, 5, 6, and 7. Now you can see there's another point where it intersects at an 8th one, but that's beyond Mary's 10-year point. And so we're really at about 7.5 years. So Bob thinks 7.5 years have elapsed.
Interesting, interesting. We're going to take a quick break at this point. We'll be right back right after Term of the Month with Stephen. And if you have a question, send us an email at the bottom of your screen. See you on the other side.
Thanks, Don. The term of the month is dwarf oddballs. The term dwarf planet was created in 2006. There are 5 recognized objects in this category. Ceres, Pluto, and Eris are the most normal. Ceres is the only one without its own moon. Pluto and Eris are similar sized and live in the same neighborhood. The other 2 dwarf planets are a bit strange. Haumea has an egg shape due to its 4-hour rotation. That's very fast. It also has a ring system, and it has 2 moons, Namaka, Namaka and Hayaka. It's about 1,442 miles, which is 2,322 kilometers, the long way. It orbits the Sun from 34 AU to 51 AU. It could have gotten the fast spin from an impact. There are 5 known objects with similar orbital characteristics, making a family of objects. The orbit is tilted 28 degrees from the ecliptic. Now, Makemake, which is spelled make for us Americans, has 1 moon discovered with the Hubble Space Telescope. It's about 891 miles, that's 1,434 kilometers across. It orbits the Sun at 38 to 52 AU. The orbit is tilted 29 degrees from the ecliptic. It rotates once in nearly 23 hours. It does not have an atmosphere. And that's Makemake and Haumea, the dwarf oddballs, the term of the month. Back to you, Don.
Thanks, Stephen. We're back. We're going to finish up this interesting conversation with a talk about relativity. So, Tim, exactly what is it?
So, relativity is this notion that time passes at different rates for different people, that there is no Newton's clock of the universe that says that this is the right time. We can all have a different idea on how fast time is flowing for us, and we can all actually be correct, and we can prove it. Just before the break, we did the Mary and Bob example where we showed that Mary thinks 10 years have elapsed, but Bob thinks it's only been 7.5 years. Both of them are in fact correct. If they had clocks on them, their clocks would be telling them you did this correctly. So what's going on, right? So the notion is we want to find out, are we correct based on that equation that we talked about earlier? So I told you that we would not need any math. We were just going to count the lines on the graph paper, the curves that we crossed over, and we came to the conclusion that we crossed over about 7.5. We can actually plug in the real numbers though, because we know what they are. So if I throw up the space-time interval again and replace the delta t for the amount of time, so the time was 10 years, but we really need the square of 10 years, so that's 100. And we know that at 2/3 of the speed of light for 10 years, you would have gone 6.66 light years, or 6 2/3 light years. And when you do that, you get something like 43, 44 is the square of 6.66. You're going to end up with like 55 and change, I think, left over when you subtract 100 from that number. And when you take the square root of that number, the question is did we get the right number? And when you do, you find out that actually it works out to 7.45. So I said that Bob thinks that he's been gone for about 7.5 years. It turns out that the space-time distortion based on his speed is exactly 7.45 years if we do the math. But remember, we didn't have to do the math. We just counted dots on a piece of graph paper, and we got pretty close.
Okay, well, yeah, so that worked out without having to do the math for the folks who work more visually.
Yep.
Mm-hmm.
So
how does all of this affect our lives?
So there are, you would think that that there would be huge impacts to it. It turns out it's pretty subtle, and that's because in order to really notice a time distortion, you need to be traveling a noticeable percentage of the speed of light. And the speed of light is so crazy fast that no matter how, get in the fastest plane that you can possibly be in, and that's still nothing compared to the speed of light. So the fraction of time that is distorted between a person staying home and a person flying on an airplane to the other side of the world is not much. But there are things that we do every day that are kind of interesting. So,
such as
using a GPS to get directions to some place that we'd like to go.
Okay.
So here's the GPS example. GPS satellites are flying high above the Earth. We are on the surface of the Earth. This actually matters. Remember, I said we weren't going to talk about general relativity, but in general relativity, gravity matters. And as you get farther and farther away from the source of gravity, that would be the center of Earth's mass, gravity gets a little weaker for you. That extra weakness in gravity causes the clocks on the satellites to tick a little bit faster. It's about 45 microseconds per day. Now, a microsecond is a millionth of a second. But the speed, because the satellites are flying at about 14,000 kilometers per hour, that speed causes the clocks to tick a little slower, but only by about 7 microseconds. So we're getting about a 45 microsecond gain and a 7 microsecond loss. And that means that the clocks on the GPS satellites are ticking 38 microseconds faster than your clocks here on the ground. And you would think, that shouldn't make much of a difference. There's, how many years and years and years would you have to go before the clocks were off by merely 1 second? Shouldn't really matter. But the better question to ask is, how far can light travel in just 38 microseconds?
How far can it travel, Tim?
The answer is just a little bit over 11 kilometers. And that means that a GPS would not be able to give you an accurate position fix within an 11-kilometer circle of error in just 1 day. So that would be completely worthless from a navigational perspective.
Sure.
So that's one example. Now there's another thing that physicists like to do in labs, which is in a particle accelerator, you can speed particles to 99.9% of the speed of light. So it's easy for them to do this with this little thing called a pi meson. They call them pions. This is a particle they can make and then send it zooming through the corridor at very high speed. They decay really, really, really fast. So they only live about 26 billionths of a second before they're gone. And so if the time is not distorted, the pion should only be able to go about 25 feet before it disappears, before it decays and is gone. But if time is being distorted because it's going 99.9% of the speed of light, the pion should actually make it well over 500 feet before it goes away. And so all you have to do is put detectors at various places down the corridor and say, well, how far did it go before we can't find it anymore? And the answer is the 580 some odd feet answer. So we can actually prove that time is in fact actually distorting due to the velocities. And when you use a GPS, you're actually counting on this time distortion to get to your destination on time.
Amazing. And to think that all this started with trying to keep ships from crashing on rocks.
Crashing into rocks.
We've come a long way, baby, as the commercial used to say. Tim, I want to thank you for coming on both last month and this month to explain these concepts to our viewers. If you wouldn't mind, you could check out our club website. The address is down, as always, at the bottom of your screen. And finishing off the program is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for June 2023? In the north, we're heading to the summer solstice. It's on the 21st of June. And by coincidence, the winter solstice is also on the 21st of June, south of the equator. On the 3rd of June, we have the full moon. Third quarter is on the 10th. The new moon is on the 18th. And the first quarter is on the 26th. Now here shown on the 1st of June, we have Uranus in Aries, which rises an hour before sunrise to 3 hours before sunrise over the course of the month. Mercury goes from Aries to Gemini and rises an hour before sunrise and to basically sunrise at the end of the month. So it's better at the beginning of the month, whereas Uranus was better at the end of the month. But at the beginning of the month, Mercury is 24.5 degrees from the sun, so that's not bad. Jupiter is in Aries and rises 2 hours before sunrise to 3.5 hours before sunrise by the end of the month. Neptune is in Pisces and rises 3 hours before sunrise to 5 hours before sunrise. Saturn is in Aquarius and rises 4 hours before sunrise to 6 hours before sunrise. And Pluto is in Capricornus and rises 6 hours before sunrise to 8 hours before sunrise, which for most people is before midnight. Pluto is not bad, I think, in June. Now, then we have, also on 6/1, but after sunset, Venus is in Gemini and moves to Leo over the course of the month and sets from 6 hours after sunset to 5.5 hours after sunset. Venus moves faster than Earth, so it gets to do weird things like that. And again, it's still after midnight, local midnight in Michigan. It's really weird. Venus has maximum eastern elongation on the 4th of June, so it's probably a little farther from the sun than usual. Mars is in Cancer, goes to Leo. It sets 5.5 hours after sunset to 6.5 hours after sunset. And that is what's up in the night sky for June 2023. Remember, we don't charge money for this show, but we may tax your brain.